Hello, I am Yuan. In this presentation, I will introduce our work on validating HMI design for increasing users' trust in autonomous vehicle. Most of the leading OEMs of the automobile have launched their own autonomous car concepts, but till now, there are no HMI design details in such a scenario. Researches have been done focusing on the single element of constructing a trustful driving experience. For example, a survey study by demonstrating simulated videos with different types of communication features in an autonomous car suggests that colored lights are not suitable for explaining the state of the autonomous vehicle, while the features in pictures are explicit. A method is necessary for the HMI design in a more comprehensive way, incorporating usage phases, autonomous driving events, trust affecting factors, and levels explaining each event from a trust perspective. In this study, aiming at creating appropriate trust in the high autonomous systems, two potential frameworks of HMI design in fully autonomous vehicles will be introduced, following two different logics, and finally implemented into virtual reality scenarios for preliminary configuration, visual realization, and preparation for the user evaluation. The most potential application scenario of high autonomous vehicle is a self-driving taxi. Starting from the user behavior analysis, the user starts to interact with the car at the moment to enter an autonomous vehicle. In the self-driving taxi scenario, users are supposed to log in their own account to synchronize their personal preference with the car system. During the journey, the users can check the state of the vehicle and the journey information at any time. This research focuses on the steps starting from getting into the car and ends at the reach of the destination. Trust is a key factor in many aspects of the autonomous vehicle HMI design, which determines the acceptance of the technology, and it is important for safe, efficient, comfortable, and enjoyable driving in general. But it does not mean that more trust the better. There is a trust curve showing the relationship between objective system reliability and driver trust. When the driver trust is higher than the system reliability, overtrust occurs, with misuse and might lead to danger, even accidents, for example, the Tesla incident. While when the driver's trust is under the system reliability, a situation of distrust and disuse arises. The ideal trust level is to keep the driver trust and the trustworthiness of the autonomous system balanced. At the popularizing phase of the autonomous vehicle, increasing the user's trust is crucial for the HMI design. The intent here is to organize the interaction modalities in the HMI design of the fully autonomous vehicle in a systematic manner, in order to create a general method for the future works in the industrial field. Two approaches have been considered in the development of the method. The first one is based on the functions of the communication content in the driving task, and the second one is based on the importance level of the communication content for the user. The word communication content refers to the information that should be transferred between the autonomous vehicle and the user. In the upper chart is the first attempt of corresponding the interaction modalities to both systems. In the lower chart is the components of the prototype proposed in the study. The core of the prototype is the HMI system with the voice communication, AI bar, user screen, and navigation screen. These are the interaction modalities. And then the autonomous vehicle is adapted from the Smart Vision EQ42. And the simulation environment is built based on IRSIM. It's an open source simulation scenario based on Unity. In order to improve the trustworthiness of the navigation screen, the visualization is built taking into consideration with the real functions of the sensors. The process of continuously exploring the surroundings to build a map and localize the car itself into it by using the data comes from sensors and pre-existing maps created by artificial intelligence and human is called simultaneous localization and mapping. This process relies on a series of sensors. This figure demonstrates a typical solution of sensor combination, and for which we can understand intuitively how the autonomous vehicle perceives the objects and the situation in around. The layout of the HMI display on board is shown in this slide. The main communication area is in the front of the car, in the forwarding direction. Regarding the visual interaction modality, there are two displays. The upper one, named AI bar, delivers information in text form, describing the states and actions of the car, and the one below is a touch screen which consists of three function areas. Two user screens have repeated functions just in case of two user mode, where users can log in their personal profile in order to get all their preferences set to increase immediately the familiarity of the user and therefore increase their trust. The navigation screen in the middle visualizes the surroundings of the car and highlights the important elements on the right with graphic user interface icons, for example, the traffic lights. 3D visualization of the environment helps to increase the trust of the user. Also, it is more intuitive for the user to sense the process of simultaneous localization and mapping. In this slide, we can see the different combinations of interaction modalities. For example, the combination of AI bar and AI voice, and also the graphic user interface navigation screen. In this slide, we can see the details of the 3D visualization of the surroundings and the highlights of the elements in the scenario. Besides the visual modality of interaction, an auditory interaction is included. An AI character called Kara is built in and is able to give a simple conversation with users by pre-establishing a series of keywords recognition inside the dictation. The female-voiced AI provides a human-like character to the car and is preferred and trusted in the previous HMI studies. The model of the autonomous vehicle is based on the Smart Vision EQ42. The operational scenario has been developed with Unity 3D, which is a game engine widely used in virtual reality driving simulation because of its flexibility and compatibility. The scenario is based on a ready-to-use simulator, AirSim by MIT. The main tools of the simulation are Unity Game Engine and HTC Vive Pro head-mounted display and the lip motion sensor in order to recognize the gestures. Questionnaires could be employed in order to get a quantitative measurement of the usability and trust at the subjective level. For the HMI design, it is also important to evaluate user comfort, especially in the context of the fully autonomous vehicle, in which comfort is one of the motivations and development focus. User comfort is a concept on both sides of physical and psychological. Fundamentally, the fatigue and stress level of user when they are interacting with the HMI should be recorded and analyzed in order to improve the design, which can be done by monitoring the physiological data of the user, for instance, heart rate variability and electrodermal activity.
Okay, I'm checking my sensors. My sensors are all up and running smoothly, thanks for caring.
Kara, give me a summary of the trip.
Here's a summary of your trip. You're headed to Liberty Country Road. The estimated time for this trip is 4 minutes and 30 seconds for a 8 kilometers ride. We will arrive very shortly at 3:26 p.m. No traffic jam have been detected along the path. Some road works are taking place in Kensington Street but won't affect the arrival time. All my sensors are unobstructed and working correctly. Enjoy your trip.
Kara, darken the windows.
Good. Now let me take you to your destination. Meanwhile, do you want me to play some music?
Thank you for listening. I hope the study is of interest for you.